Great to be here. Actually, I expected to see at least one image of a CO2 plume, but maybe that's for next time to put it into ask people what it actually is. I want to talk about TANGO. TANGO stands for the Twin Anthropogenic Greenhouse Gas Observers. And actually, those are two CubeSats. Two CubeSats flying in the formation, and the time difference is less than 1 minute. And one measures NO2, the other one CO2M. And this idea is actually developed in the team, and you see here the team at the bottom. That is, first I want to mention the startup company, Delft Space, TNO. What about TNO, which are responsible for the spectrometers, and then we have KNI and SRON for science. We have to talk about climate. I show this slide with different topics related to climate, and each time I give a presentation about TANGO, I add one keyword there. Last week I was in Wageningen, and I added climate justice and fast fashion, and for you I added here impact of climate on astronomical observations. And all that, these different things are related to climate. It's such a diverse topic, but it all goes back to one problem, and that is the rise of the global mean temperature. Here you see a diagram from the IPCC, the most recent report. This is from the report on the physical basis of global warming, and what we see here is the change in temperature, in the mean global temperature from the pre-industrial period to today. There are many lines. First focus on the solid black line, and that is the total temperature rise because of anthropogenic activities. So we see this huge increase in the last decades, and we are currently at a temperature which is 1.3 degrees warmer than during the pre-industrial period. Now you can ask what are the different contributors to that temperature rise, and you can split that up to different atmospheric constituents, and those are the different lines that we see here in this diagram. And the most important one, that's CO2, and that's the, I'm actually colorblind, but I think it's pink. That is the upper one, this line, which follows nicely the solar line. And CO2 is the most important greenhouse gas, and it contributes to this 1.3 degree, which we currently have, with 1 degree. So 1 degree warming is because of the increase in the CO2 concentration levels. The second most important greenhouse gas, that's methane. And that is the green line, close to the, over here. And the contribution of methane is about a quarter of that of CO2. And then we can go through all these lines, but those are the two most important ones. And the other one I will mention, that those are aerosols in the atmosphere. Aerosols, they reflect solar light, and they do not warm, but they cool the atmosphere, because we get rid of solar light due to the presence of aerosols. And what we do see here in the curve of the aerosols, that's the cooling curve over there, that there's a kind of tipping point around the year 2000. And we believe that this is because of our effort to improve air quality. Because typically aerosols is an issue for air quality, but they are also climate relevant, as we see here. And that has quite an interesting aspect. Assume you would keep the CO2 concentration in the atmosphere constant, only because of the fact that the air gets cleaner, the atmosphere will warm up in the future. Although we keep CO2 and methane constant, only because of the fact that the cooling is less. This predicts not the best for the future. However, we are also far from keeping the CO2 concentration and methane concentration constant in the atmosphere. That's what we see here in this view graph. Another picture from a recently published IPCC report on climate mitigation. And what we do see here is the greenhouse gas emissions on the y-axis for 3 decades. And it's split it up in CO2 in the bottom, and methane in red, and other greenhouse gases. And what we do see is that there's a continuous increase in our emissions. We are far from actually reducing our emissions. And actually, I gave the first talk about climate-related issues in 1996. I was a PhD student in Germany, and went there to a kind of district government, and you see I was not successful at all. It increased and increased since then. So we are in a crisis. crisis. We have a climate crisis, and we have to do something about that. And the only thing, and there are two things that we have to do. For sure, you have to work on the solution, but another important thing is you have to know what your current situation is of the emissions. How much do we emit now? How much do we emit in 5 years from now? Just to adjust our mitigation strategies to the real situation. And therefore, we need to measure the emissions. And there are two ways how we can do that. From space, there are ways to do that, and I want to illustrate that in on this slide. On the left, you see TROPOMI. You've heard about TROPOMI already. That is a methane plume in Turkmenistan, and here at the bottom, each triangle is actually an oil production facility. Over there, it was a big event, and they have released a lot of methane, which led to this huge plume. This is a super emitter, we call that. These emitters we can see with instruments like TROPOMI. But when the emission is weaker, like we see here, for example, over there, it's already hard to detect the plume. You can think of the smaller the emissions, suddenly you won't see. We can see this emission when we go to the smaller scale, which you see here. These are actually airborne measurements, but you can also have satellites which measure the plume on that scale on a few tenths of meters. And what you do see here is the emission plume from that facility, and you see all this turbulence in the atmosphere back in the shape of the emission plume. And in doing so, we can really go to smaller emissions. And there is no contradiction between these two different types of measurements, but actually they are complementary. And I want to illustrate that on that slide. It goes back to a paper published by a colleague of mine from Mars. What we do see on that slide, those are the methane emissions from TROPOMI, averaged over about 3 years, a bit less than that. So you see a lot of features, the global distribution of that. We see the tropics, a bit more methane also in Asia. But we can also zoom in certain areas. And what Bram did, he looked into the data around Buenos Aires. We already have seen it in your slide, a few words about that. You see clearly the emission of that city. So you can derive from those data emissions of that city, and if you do so, you see, oh, this city emits about 2 times as much as reported in the so-called inventories, which reports the emission of different countries. So satellite data can be used to characterize that. But what kind of facility in that city actually caused that emission? We don't know. We don't see it actually on that scale. And that's why they have pointed a target emission which really goes into this high-resolution domain. And they found that 60% of the emission of that city, Buenos Aires, came actually from the landfill. Not only from the landfill, you may think this is a park, it's not a park, but part of the landfill is covered, and the emission actually comes from the open part of the landfill. So they could really trace back not only to the facility, but also on subscales of the facility which emitted methane. And exactly that is what we want to do with TANGO. We have on one side the global survey emissions, but we want to have a targeted emission which zooms in a certain area and provides us detailed information down to the facility level of the emission. And therefore, we have these two CubeSats, 60 liters, 60 units, and they will provide collocated measurements of CO2 and methane, and in addition NO2. So we have the NO2 spectrometer that measures it visible. It's also used for cloud clearing. You can imagine the emission that takes place in the lowest part of the atmosphere. We call that the tropospheric boundary layer, the lowest 2 kilometers about. And you can only see that if it's clear sky. So we have to know that the observation area is clear sky, and therefore we also use the visible spectrometer. And then we have another spectrometer which measures in the what we call the shortwave infrared, the 1.6 micrometer band. And I will show you later why this is such an interesting spectral range. The question now is, and can you start the movie or can I? Yeah. The question now is, why do we want to measure NO2? NO2 is not a greenhouse gas, not at all. The reason is shown here in this movie. It's actually model simulation, and it shows the CO2 concentrations, how it changed with time over the US. And what you think it's a very busy figure. Actually, the background of CO2 is pretty large because its lifetime is so long, and the variation that we see is pretty tiny, in the order of 10%, 1–2%. The first thing what we see are weather systems. The cycling, they pick up the CO2 emissions from some locations, and then they transport these enhancements over the continent and over the ocean. So you say, cool, let's measure these kind of features, and then we try to calculate from that emission. But we can't do that, it's too complicated. We cannot link the weather system patterns that you see here to the local emissions over the Earth. But what we can do is to measure these tiny emission plumes close to the coast, to the east and west coast. You can see them here, for example, very clearly. They also pop up here at the west coast. Those we can measure. And now we have a problem. We have long-range transport and very localized emission patterns. How to disentangle that? Because one thing we want to measure, those are these local enhancements, and there's one thing we definitely do not want to measure, that's long-range transport. And there NO2 becomes an important tool. We have a power plant, and the power plant, that's a combustion process, right? So oxidation takes place, that's why we get CO2, for sure. But not only that, we have also nitrogen in the atmosphere, and that oxidizes in the combustion process to NO. NO lives very shortly, that is actually also emitted at the power plant. It lives there only, I don't know, half a minute or whatever, and then it's converted to NO2. So actually what we do see in the emission plume, that is CO2 and NO2. That's illustrated in this view graph for a power plant here in Schwalbe in East Germany, one of the bigger ones. And you see the plume in the 3D animation below, and then you see the measurement of CO2, which is quite noisy and suffers from this long-range transport. And then on top of that, we see NO2. NO2 only lives for 2–3 hours in the atmosphere. So it stays in the plume, but it then oxidizes further and disappears. So we don't have any background, and a very distinct feature of NO2 in the atmosphere, which shows us where the emission plume is actually located. So it helps us to find the emission plumes in the movie that we have seen before. And just to show you that it's real, again, TROPOMI. We see here some pictures from, I think it was from the first 2 to 3 months during the commissioning phase, and we got those data in NO2. You see these emission plumes, and they are all related to the emission from the power plant. So it really works like that, so that's great. I promised to show you what we actually want to measure. We want to measure absorption features in the atmosphere, for sure, spectroscopy. And we have to go to the 1.6 micrometer band, because there we have two absorption features very next to each other with similar strength, CO2 and methane. And from those spectral features we derive the total amount of CO2 in the atmosphere. So no profile information, but the total amount of the greenhouse gases. But as we know that they are emitted at the surface and the plumes take place in the boundary layer, we can actually hide information. It's not so relevant here. There's one big caveat in the whole thing, and that is that we have to measure it very precisely. In this figure, you see a simulation of a plume, which is then convolved to the resolution and sent to the resolution of our instrument, 300 meters, and the wind goes from left to right. So you see here nicely the plume. There's no noise in the image. So that's great if reality would be like that. However, we have noise because of the measurement noise. If we have 0.5% of noise in our image, you still can see the plume. That's okay. With 1%, it already gets more difficult. Still, there is the plume feature present, but if you go further, 1.5–2%, suddenly the plume is gone. So precision is the key parameter, such that we can detect these tiny enhancements on top of the atmospheric background in our CO2 plume. So how can we achieve that with the mission that we have? And the great thing about it, the mission, is that we have an agile platform. Agile means that because there's some reaction wheels on the platform, you can rotate the satellite around these 3 axes. One is a pitch maneuver, a roll, and a yaw maneuver. And what we do see here is a pitch. So what we do is we rotate the satellite towards our target, approaching, then we follow the target for a certain period of time, a second about, and during that we enhance the data creation time. We collect more photons, and that makes our measurement more precise. Now, that's a cool thing about these CubeSats, which have this pointing mechanism. But we can also look to the side. That's a roll maneuver, about 30 degrees to the left and to the right. And if a target is not at the sub-satellite track, but a bit to the left or to the right, we still can observe it. Which means that with that mission, we can observe about 300 targets in 4 days, which is quite a good number for such a mission. So everything is there, and now I want to show you a bit. Can you start the movie? How such a measurement finally looks like. We call that end-to-end simulation, and it can keep you busy for years with this kind of exercise. You try to simulate the whole chain of your observation. And we start with the sea. What you see in the background is the surface reflectivity in around Jenswalde again, and the bloom which is emitted. And you see here nicely the turbulent atmosphere which let the plume meander through the sea. Which, and then during night, we are now at, so yeah, now during night the atmosphere becomes stable again, so preferably you would measure during night because you have such a nice blue. Unfortunately, we measure reflected sunlight. So we have to deal with these turbulent features in the blue. So with that, we go further and we simulate the whole performance of our instrument, starting with the orbit that we simulate, the light which illuminates our satellite, the optical system of our instrument, then the calibration of the data, and finally the retrieval. And that's what you see here. On the left you see what we retrieve from the surface reflectivity over the area, which is a byproduct. What interesting is the dark areas, which is this bluish one, those are forests, which reflect a little light. In the center there's our power plant. We have the mining around it. You know, it's a coal-fired power plant, so they get the coal from the surrounding. And then look to the right. That is then finally our product that we deliver. And you nicely see the snapshot of our plume starting here in the center. The emission takes place, and then meanders to the left. But you see also a lot of noise in the image. And the interesting part of that simulation is, for example, in the upper part, you may think that there's a feature, but it is not really a feature. It's only that the scatter of the data increases there because we have lower signals. The surface is dark. But the plume here itself, that is a clear signature further than interpret live data. So that's TANGO. And we already busy with what's next. You know, when you start a mission, you always have to think of what are the next steps. And that is, you want to have a mission which improves or which has a better detection limit, can observe even smaller sources. We already mentioned that. And to illustrate you how we think about that, how to improve TANGO, I've prepared here this figure, where we see on the y-axis what we call the detection limit. That is the smallest sources that we can detect for a certain mission configuration. And we see that for different resolutions, going from 60 meters to 300 meters, and for different precision of our observation, where we have a very precise observation on the left and a less precise observation on the right. And our TANGO design is located around here. We have a 300 meter resolution. Precision of our data is about 0.5%, and we don't see obviously, but that's a typical reference value. And we can say that we can detect CO2 plumes or emissions of power plants which emit more than 2 megatons per year. Which means that with that concept we can measure about 70% of all anthropogenic emissions from power plants. That's the idea. But what is about the other 30%? Now, we have to improve our detection limit, and there are 2 ways how we can do that. Well, there are several ways, but the first one is that we keep the resolution and we try to measure more precise. Then the detection limit gets better, right? That's obvious. The more precise you measure, the more you see in your image. But is that really a good idea? Actually not, because if you measure more precise, also your accuracy must be better. Your systematic errors on the observations should be reduced as much as possible. That leads to expensive and cost-driven designs, and that's not the way how we want to go. The idea we want to go is that we go in the vertical, that we improve the resolution of the instrument, that we can see more features of our plume, and doing so to improve our detection. This is TANGO next generation, and we hope all that we can realize. So where do we stand? Where do we stand today? We are actually ready to go. We have designed the instrument, we have the algorithms designed on the conceptual level, and we want to start to manufacture the instrument in the second half of this year, hopefully, but definitely at the end of the year, beginning next year, we will start, because we want to launch the mission in 2026, and that is related to what is called the global stocktakes. You may have heard about that. The points will collect all the information about our emissions each 5 years. The next one is in 2028, and we want to contribute to that. Thank you.
Yeah, so you mentioned that you can use nitrogen as a trace gas for CO2. Is it always the same amount of nitrogen that comes out of some combustion, or do you have to know what kind of power plant, or is it cars, or forest fire?
If that would be true, if the, what we call the emission ratio of NO2 to CO2 would be constant, if the emission ratio would be constant, then we shouldn't measure CO2 anymore, only NO2, and then we're done. But that's not true. That's not true. I mean, this emission ratio really depends on the combustion process, how you generate the energy, how you filter your emissions. So it really changes from power plant to power plant, and combustion process to combustion process. Actually, quite interesting. Methane. If the methane is emitted by a combustion of high temperature, more NO2 is released. If you have a fire of low temperature, there's very little NO2 release. So it really depends a lot on the process. But the idea in itself is not so bad, actually. Because if you look at one power plant, for one specific power plant, this ratio is probably constant, because it belongs, it's a key parameter of that facility. And you can say that you can get more data using other satellites which measures NO2, and you use the emission ratio that we derive from TANGO to scale those observations to CO2. That's a bit some ideas we have to further get more data.
Since you do this maneuver when you pass over a power plant to kind of point at it to get multiple images to reduce the noise, do you also get from that some kind of little short video clip of the emissions, or is it just so you have to reduce the noise? It's too noisy to take individual frames.
That would be cool. First of all, then you need several readouts, which we integrate the signal during the scan. That's one thing, and it's only 1 second. You know, that's not so much. But you're touching on quite an interesting topic, which keeps me busy at least. I really think, you know, there's one big uncertainty we have, and that is when we want to translate the emission plume that we do see in our data to the emissions, we have to know the wind speed, because the wind speed tells us how the emission is distributed in the atmosphere. And the wind speed, you may think, we have all these meteor data, all this forecast data, but it's one of our biggest error sources in the estimation of the emissions. But if you have 2 images of the same, with say a time difference of a minute maybe, the plume changes in shape and tells you something about the atmospheric transport, and maybe can be used for wind forecasts. So, but those are all ideas, pretty cool ideas.
I was wondering about the plans to go to higher spatial resolutions, and whether there's a certain limit beyond which it makes no sense. in the direction. I was thinking of the size of turbulence elements.
Yeah.
And if this, I mean, if you reach that domain, you have to average anyway before you can do anything with it. So I was wondering whether the 60 meters you were targeting are already in that domain or still not.
I don't have an objective answer to that. I'm from TANGO. If you ask people who build the instrument with 10 meter resolution, they think differently about that. I personally think, theoretically, if you would know the atmospheric transport perfectly, the higher the resolution, the better. But that's not the reality, right? Because the advantage of going to a higher resolution means that you want to measure this very strong enhancements close to the source. There the main information comes from, because you can resolve that. That turbulence is important. Not only turbulence, look at a power plant, you have condensation close to the source. That makes the whole data interpretation extremely difficult. Also, to describe how the atmosphere behaves on that scale is a big, big challenge. So I believe that if you manage it with 300 meters, I'm very happy. But I do personally not believe in data interpretation on the 10 meter scale. But that's my personal view.
Is there any manual in the satellites, or you just put it in orbit and they just go around the globe, or you point them in the Netherlands only?
They are what we call in a sun-synchronous orbit, so they always fly over the poles, orbit height of 500 kilometers. So it's not that like a geostationary satellite which always looks at one location, but we make a round around the Earth, and the Earth will change the local satellite. That's why we can observe source all around the Earth. But for sure we can rotate the satellite as described, and I'm not the expert on that, but probably if there's some maneuver they have to take because of debris or whatever, they will do that probably. But there's
go back, like I saw something. Can you go back there? Can you see something interesting, like let's go back?
No. So we have to go on. Yeah.
Any other questions?
It might be a bit of a silly question, but if you different wavelengths probe different parts of the atmosphere, I don't know if the wavelength range is large enough, but could you maybe, would it be possible to sort of construct the 3D measurements from the fact that you can use several the lines next to each other, or is that spectrally way too close to each other?
Okay, that's an interesting question.
Could you please repeat the question?
Yeah, the question is if you can infer actually altitude information from the spectral domain, because you have different absorption depth and lines. Now, we do know that this can work in the UV, for example, where light is scattered back to space at different altitudes depending on the wavelength. And that's why we retrieve their own profiles. That's a common feature. In the spectral range where we work, actually there's no scattering. So your light always goes through the atmosphere. There's nearly no scattering. There is a little bit, but you cannot use it for that kind of trip. So it goes through the atmosphere and it's reflected, preferably at the surface, because clouds right? So the light path always tries through the atmosphere. But the question is for sure not silly, because you may know, I don't know, if you studied molecular physics, you have line profiles, and the profile and the line shape depends on temperature, and theoretically you can use the lines individually to retrieve some altitude information. But the resolution and the precision is not good enough for that.
What are its TANGO work?
Sorry?
What are its TANGO work? What are its TANGO work? Like the spectral resolution?
The spectral resolution is, I don't know the resolution color, it's 0.15 nanometer.
Okay.
Yeah.
You do a passive measurement of the incoming light into the instrument,
Yeah.
which is a function of the solar emission, solar intensity, reflectivity of the Earth, and the atmospheric absorption.
Right.
How do you untangle these different components? You know, you see a difference, but is it due to the atmosphere, is it due to the sun, is it due to the Earth surface you're looking at?
Yeah. First of all, the surface is not our problem because we retrieve the surface as well. So the spectrum contains also information about what we call the diversion and reflection at the surface. The solar spectrum. There are satellites which do actively measure, once in the orbit, they point to the sun as a calibration source, right? And this is particularly interesting in the visible and the UV because there the solar activity is really shows a clear variation. In the short-wave infrared, the variation is not so big. So you can use, actually, don't need to do solar measurements each day. That's not necessary. And you can use other measurements which also measure the sun. So that can be captured. What is also important that the lines, the Fraunhofer lines, which probably you're referring to in the spectrum, they do lie at different positions, though they do not really interfere with our telluric absorption patterns. So that works actually. We know that from other satellites, which have followed the same concept.
I believe TROPOMI had also a sensor that measures the incoming sunlight.
Yeah, that's what I meant.
From the top.
Yeah. No, not from the top. Actually, when you come from the eclipse, there's a solar port which looks towards the sun. So once in the orbit, you point toward the sun and you measure then the solar spectrum. Or once in a day, I think. Not sure if they do that each orbit. You can do that, but you know, in the short-wave infrared, actually, what is good about that is not the knowledge about the sun, but that you can calibrate your instrument with that actually. Because then you calculate, use as a measurement the ratio of the reflected light divided by the sun. And doing so, several errors cancelled out. That's why this trick is used. But actually, we do know from other satellites that in the short-wave infrared, it's not so important.
So let's thank Jochen again.